Okay, so my first problem was 55, and it reads, you're driving along at 25 meters per second with your aunt's valuable antiques in the back of your pickup truck when suddenly you see a giant hole in the road 55 meters ahead of you. Fortunately, your foot is right beside the brake and your reaction time is 0. Part A asks, can you stop the truck before it falls into the hole? So I thought first to find the forces that are acting on the truck, and we have our gravity force, our normal force, and then the force of friction from the tires on the road that is decelerating the truck. Um, so since we don't have a mass for the truck, we can't really use our normal force to help us with friction. With friction usually equaling the normal force multiplied by the coefficient. We have our coefficient as 0.8 as it's given for rubber on concrete. So we're able to use that later to find acceleration. So I have our net forces equal to our kinetic friction, and then you can have your force equal to ma. And since we have now our normal force, our Fn, multiplied by our coefficient equaling ma, because we have our F equals ma up here, we can substitute our normal force for ma, just because it's another force, it can equal a mass times acceleration. So now you're left with a mass on each side, and you're able to cancel out the mass. As our acceleration is gravity, we can substitute that a for g. So we have our coefficient, which is 0.8 multiplied by gravity, and we have 0.8 multiplied by 9.8 gets us a equaling 7.84 meters per second squared. And this will be our maximum acceleration that we need um, to stop. So like we don't need any more than that, or um, if we have less than that, then we are able to like uh, slow down quick enough to not hit the hole. So we have our so the reason we found that is so we can compare our acceleration, our actual acceleration to it. And as long as it's less than that, then we'll be good and we won't fall in the hole. So we have our velocity function, or velocity equation, sorry, as your final velocity squared equaling your initial velocity squared plus 2a change in x. We have all of these except for a, which is what we're going to try and find. So I just rearrange the equation by bringing our initial velocity over here and dividing it by our 2 and by our change in x. We have all of those. So now we can plug in 0 for our final because we want the truck to stop. We have our 25 meters per second, which is our initial velocity, and then our 2, and then our change in x needs to be 55. As long as we stop before the 55, we'll be okay. And when you plug those in, you get your acceleration is 5.68 meters per second squared, and that is less than 7.84, so we are good. We will be able to stop before the truck hits the hole. And then part B asks, if your answer to part A is yes, can you stop without the antique sliding and being damaged? Their coefficients of friction are US equaling 0.6 and UK equaling 0.3. It gives us the kinetic friction coefficient, but we really don't need it. So we're only going to be using the US for this part, our static. So we have kind of like we did up here, our net force is being our static friction. Same thing we did up here, we just plugged in our ma for our normal force, and we can change the a to the g as gravity is our acceleration. So we have our us multiplied by our g equaling our acceleration because we canceled out the masses like we did up here. And then you get that your acceleration needs to be less than 5.88 meters per second squared to not have any of the antiques slide around. And we know that our acceleration would have been 5.68, so it's less than 5.88, which means that our antiques will be okay and they won't be damaged.